So today we are going to reintroduce the concept of a logarithmic function. We talked about in section 3.1 an exponential function, and we said that exponential functions were one-to-one, which means that an exponential equation represents a function and its inverse is also a function. And since they're one-to-one, that means that they have to have an inverse function, and that is what we call a logarithmic function. A log function is defined as the inverse of an exponential function. And so the definition of a logarithm is this, and really for no other reason than this is what we decided it's going to be. But the definition of a logarithm is that y equals log base b of x. That's how you would read that out loud. You wouldn't say log b of x. You have to say the word base, because if you say log 2, that's the log of 2, and that's a different base. So it's the log base b of x is equivalent to saying b to the y equals x. Now I want you to look at how this is set up. So the logarithm was equal to y, and y now becomes the exponent over here. The base of the log is also the base of the exponential. So that is exactly how I remember to rewrite these. This used to take me a really long time to kind of grasp. And so the one thing that I've come up with that is really helpful to remember is this idea that logs equal exponents. And that is always how they're going to set up, is that logs equal exponents. And that helps you to retrace your steps and kind of rearrange what you have there. And that's just what that second box there at the bottom says as well. So if we look at some examples, these first couple here, we want to rewrite each equation in its exponential form. So again, here's how I look at this. The base of this log is 5. So that's going to be the base of my exponent. Logs equal exponents. So that means I need to raise this base to the power of 2. And then at that point, the only thing left that I have not used is the x. So that's the last thing that goes there. So x is equal to 5 to the second power is how we would write that. Looking at example B, the base is b. The log is equal to the exponent, which is 3. And the only thing that I've yet to use here is the 64. So b to the third equals 64. Take just a moment to write down example C. See if you can figure out what that one is going to be before I write it down. Three to the y equals 7 is what we should be coming up with here. 3 is the base. The log is equal to the exponent, so that becomes y. And that is equal to 7 because that's the only thing that's left. We can do this in reverse as well. We can take each of these exponential functions and write them as a logarithm. So again, start with your base. The base is 12. So, whoops, I'm going to say the log base 12 of, I'm not sure yet, but I do know that a log has to equal an exponent so that the 2 is going to go over here. That means I must be doing the log base 12 of x, okay? So here, this is going to be the log base b of, it can't be the 3, so it must be the 8, and then the log is going to equal the exponent, which is 3. So see if you can try that last one really quickly. Go ahead and pause it if you don't have it quite yet. But this would be the log base e of 9 equals y. And now one thing you may remember from last year that we'll talk about here soon is that when we see this log base e, you may remember that that's a special kind of logarithm. That is a natural log, and you can write that ln. And so the nicer way to write this would be the natural log of 9 equals y. Okay, we don't typically see that written down as the log base e. The other one that you might remember is if I write just log with no base, this implies base 10. That's the common log. So your calculator just says log, So your calculator is the common log, it's a base 10, and then it also has the natural log, which is a base of e. Okay, so using these same properties then, we can evaluate logarithms. And let's think of this in this way. We have sort of this mystery piece of information. That expression is going to be equal to some unknown value. Remember that logs equal exponents. So what this is saying is when the base is 2, what is the exponent that gives me an answer of 16? Well, 2 to the 4th power is 16, so that is what this logarithm is going to be equal to, okay? So the same thing here. If I look at b, 7 to some power is going to equal 1 over 49. Well, the only kind of exponent that will take me from a whole number to a fraction would be a negative exponent, so I know it's going to need to be negative. I also need the 7 to become a 49, so that's how I know that it's going to be negative 2. And again, this is because 7 to the negative 2 power equals 1 over 49. That's why negative 2 is the correct answer. Okay, 25 to what power would equal 5? That's what the log base 25 of 5 says. This is 25 to some power equals 5. Well, don't forget that we have negative exponents that can help us create fractions or flip over fractions. They're going to take the reciprocal. And then we also have rational exponents, fraction exponents, and those do roots. So since the square root of 25 is 5, this has to be equal to 1/2. And again, that's because 25 to the 1/2 power is equal to the square root of 25, which is 5, which is what we were trying to accomplish there. So that is why the answer is 2. Similarly, this expression here on example D says 2 to some power is equal to the 5th root of 2. That would be 1/5, because that's what the 1/5 power does, is it takes the 5th root. So those are tricky. Those are going to take some practice of looking at your negative exponents, when those are going to come in handy, and looking at your rational exponents and when you might need to use those. Excuse me, I'm yawning. Okay, so the last thing that I want to talk about today is just some basic logarithm properties and kind of like the undoing bits of each other. So since logs are exponents, they have similar properties that can be derived from the exponent properties. So these properties involving 1 are really helpful. So I have the log base b of b has to equal 1. Because if I say that, I say b to what power equals b. Well, the only exponent that's going to equal itself is going to be 1. So the log base b of b is going to be 1. Log base 2 of 2, 1. Log base 5 of 5, 1. Log base 1/2 of 1/2, 1. Doesn't matter. As long as the base and whatever you're taking the log of match, the answer is going to be 1. Secondly, if I take the log base b of 1, that has to equal 0, because b to the 0 power is always going to equal 1. And so that's any log. Log base 2 of 1, log base 10 of 1, log base 0.56 of 1. The answer is always going to be 0 in that case. Okay? And then lastly, these inverse properties. Remember that logs and exponential functions are inverses. That means they undo each other. That's like saying the x squared and you take the square root. You just get x. Similarly here, if I do the log base b of b to the x power, these two things undo each other and all I'm left with is x. Or we could do that in reverse. B to the log base b power, these are both going to undo each other and we're just left with x. So let's look at a couple of examples down here. And then this is all that we have to look at for this first part of this section. So the log base 7 of 7 is one where the base matches what we're taking the log of. So hopefully you see that the answer here is going to be 1. Example B, the log base 5 of 1. Anytime you take the log of 1, it doesn't matter what the base is, the answer is going to be 0. Now here for example C, I have the log base 4 and I have 4 to the 5th. The bases match, so they undo each other, and all I'm left with is the exponent, which is 5. Similarly, the base here is 6, the base of the log is 6, so we just end up with 9. Okay, so that's just kind of a review of how logarithms work, how you rewrite them, how we can work them back and forth, and this inverse property, how this works with an exponential function. So those are the main things that you need to focus on today, and that is where we're going to stop.